Hi, I'm Ting Chao Chou, the one who derived the median effect equation and introduced the median effect plot for general dose effect analysis. This theory has recently been called the unified theory of the mass action law. I'm also the co-developer of the combination index theorem for drug combination with Professor Paul Talalay of Johns Hopkins University School of Medicine. As is well known, drug combination has been widely used in treating multiple diseases such as cancer and AIDS. However, many researchers, when they conduct their drug combination study, did not do it right or did not interpret the data correctly. So I'm going to present the method and theory of my method. Let's see. Last year, AACR meeting in San Diego, I gave a mini symposium on drug combination. This year, AACR meeting in Denver, I'm going to present a poster also talking about drug combination as shown here. The method of Chou and Talalay has been widely cited so far, 1,820 in 381 different biomedical journals. Today, I'm not going to spend too much time going through all the theories, but here you can find the theory as well as application, the sample data analysis. These are major references with examples. One is advanced enzyme regulation I just mentioned. The second one is JNCI paper, which is highlighted with editorial, which give crude data for 2 and 3 drug combination. I may give this later as an example for presentation. The pharmacology review article published in 2006 is my lifetime theoretical work, 35 years of work. It's cover every aspect of drug combination studies. And the computer software, CompuSyn, is the 3rd generation software. The 1st generation published quite over 20 years ago, written by my son, Joseph. And later, the 2nd generation published as a CompuSyn, written by Michael Hebel of Cambridge, England. The 3rd generation computer software called CompuSyn, which is written by Nick Martin of MIT. This just published recently. And recently I published a review article in clinical journal Leukemia and Lymphoma, which is abbreviated review, also give examples. The CompuSyn is not only for drug combination, but also for general dose effect analysis, such as determination of IC50, ED50, LD50, and so on. Here are the website, and can get more information. The experimental design is the simplest way for 2 drug combination, drug 1 and drug 2. From preliminary data or from literature, you get approximate IC50 or ED50, and use dose range below and above it for drug 2 also. So the dose range will cover broad spectrum, will not be skewed like inhibit only 20-30% or inhibit 95-99% like that. My recommendation is a constant ratio experimental design, which you make a mixture of drug 1 and drug 2. Make a mixture at high concentration and serial dilute. So no matter how you dilute, it's constant ratio because it's a mixture. And also, one recommendation is usually you don't delete the data in the middle, which is not right to do that. But to the extreme, if the dose range is too high, it's not accurate to measure, you can delete the data point. Or if too low, is below your sensitivity of detection, you can also delete the data. It does not need to be always a particular ratio or particular range. It's only the most reasonable recommendation, because when you have 80-50 ratio, the contribution of each drug to the mixture is about equal. So, and another thing, recommendation is do this single drug alone and the combination in a single day or a single experiment, because if you do one part today, another part next week, everything is not identical. So everything needs to be compared under the identical condition. So drug 1, dose effect curve, drug 2, and combination should be done at the same time. You don't need to be always twofold dilution. This is the common serial dilution in pharmacology, is twofold dilution. And also the combination ratio, this only recommendation for 80-50 ratio, but you can do any other ratio if you want, if you have special reason to do it. And also you can do, if you have time, and you can do Latin square or checkerboard, though you have different ratio combinations. So there's a lot of flexibility. Here I have 1, 2, 3, 5 concentration. It depends on the assay. You usually do the duplicate, and usually you can have 6, 7 concentration if you want. Even the data will be even better. And usually we do duplicate, even sometimes triplicate, to gain and enter the average data to the computer. So now I'm going to another aspect. I shrink this. Okay, I go to the practical aspect. This is the CompuSyn software logo. You click it, it's open, and this will come out. If new experiment, you just click new experiment. You recall from the previous experiment you store in a disk or a memory card. You can call it out to do the analysis. So if you have new, now to save time, I like to recall the old save the data. For example, this particular file, and open it. Okay, it tells you this actually what you put into the computer, the name of experiment, the date, and your description, conditions, and so on. And then enter drug 1 as a new drug, like the drug 1, this fludiron. And then you finish, and then you go to drug 2, and this panoxytriol. And for example, if you enter data wrong, you want to correct, you can click like drug 1 is error, you can want to editing, the entire data pop up. This is drug 1 fully long, what unit, abbreviation. All you enter was the dose effect, the concentration effect. You put in all the data, you have 8 data points you put in, and then you finish. And then if you want to delete certain point, just click it and delete, or you want to add new data point, just do like that. And when you finish, just finish, then just go back. You want editing the combination, You want to edit it, the all pop up, and then this you enter the save the data. In this case, combination ratio is 1 to 1,000, and so if you add drug 1, this drug 2 and total will automatically pop up, or you can put the total drug 1 and drug 2 automatically pop up because they know the ratio here already. And you can edit when you did something wrong, this the same way, and you finish, it go back. Okay, let's come to here. Okay, so now you can save your let's generate the report. Computer all the data, single drug A, drug 1, drug 2, and combination. The data are all there, and you click generate report. And sometimes you have more than 2 drugs, you have 3 drugs, 4 drugs, for example. You click drug 1 and drug 2, you say okay. And combination is this. Sometimes you have different other combination, you can also click, but here we have only 1. So we say okay. And they will have option to select what you want to print out in report. For example, I want log FACS plot also, and I want log FADRI plot also. Polygonigram I cannot click because for more than 2 drugs, 3 drugs, 4 drugs, so it's not applied, so I don't click. And they say they generate, I say okay. Now it takes 1 second, generate entire report. So this actual printout look like this title, date, and the file name, the description, drug 1, drug 2, and mixture, and you have 8 data points, dose and effect, and when you enter dose and effect, it tells you how many data points, and also it gives you 3 parameters, M, DM, and R. M is a kinetic order. In other words, in my median effect equation, it means the shape of dose effect curve is sigmoidal or hyperbolic or flat, or what I tell you the shape. The DM is IC50 or ED50. It's a median effect concentration, and it tells the potency. R is linear correlation coefficient of the median effect plot. It tells you, is your data really fit the theory? It applies to mass action law or not. In this case, 0.99, almost 1, almost perfect data. So it tells you 3 different things: the shape of dose effect curve, the potency of the compound, and how good are your data. If lousy data, you may got 0.9, 0.85. If lousy data, you really have reservation on your result and interpretation. If data no good, the conclusion should be no good. So this is drug 1. So drug 2 also, the dose effect curve for drug 2, dose effect and parameter, and combination is a constant ratio combination 1 to 1,000. This mixture to computer, it doesn't matter is a mixture or how you combine it. You just take your data, and actually this mixture can be considered as a third drug. You know it's a mixture, but it can be considered as a third drug. Also calculate MDM R value, and the computer automatically generate dose effect curve. Automatically scale with proper scale. All these curve can be linearized into straight line by my so-called median effect plot, which is used widely. It linearized curve into straight line. The intercept, x-intercept, is log DM, median effect. So you can calculate from this plot, it calculates DM value. The slope of this line is the M value, the shape of dose effect curve. When it's steep, it's sigmoidal curve. If shallower, it's a hyperbolic curve. For example, it tells you the shape of those curves. And fitting all these parameters into my equation, Zhou-Tarare equation, it calculates combination index, which tells you how much synergism or antagonism or additive effect. Here is a computer simulation from 5% inhibition to 97% inhibition, all across. What's the CI value? The CI value, if equal 1, is additive, smaller than 1 is synergism, greater than 1 is antagonism. In this case, you can see at very low concentration, you got antagonism, and then synergism above 45% inhibition here. In cancer research, it's important to see that high effect level synergism or not, because it's not useful to treat patients to inhibit tumor 20-30%. But the next day it grows back, actually. You need to cure or treat the cancer, you need to inhibit or kill 95%, 99%, 99.99%. So it's not equally important. So don't be alarmed by antagonism you see here. And the computer also calculate actual combination data point. This is actual data point, it calculates CI value. How much synergism, how much antagonism. In a graph, so-called F combination index plot automatically. At the low concentration, you got some antagonism. So this line is additive effect. Below this line is synergism. Above is antagonism. So it tells you entire spectrum, how much is synergism, how much antagonism. And sometimes the scale go out of scale, and computer also automatically generate log CI value, so it's condensed logarithmically, so won't be the out of scale point you can still notice. Another thing I want to point out is, if you see FACI plot, antagonism is very high, like a 5 or 10, and here synergism is 0 to 1. This antagonism is 1 to infinity. So not arithmetically, you don't be alarmed by because this scale is totally different. 0 to 1 for synergism, 1 to infinity for antagonism. Okay, so the computer generate all this, simulate actually with the constant ratio design at different effect level, how much drug 1 require to get certain effect. Like 50% require this much drug 1, require this much drug 2, and also it calculates dose reduction index, which means when you have synergism, you can reduce your dose and yet obtain identical effect. So dose reduction index did not tell us exactly synergism. CI value tell us synergism, but dose reduction index is very important in clinical situation, because when you reduce your dose, allow to reduce your dose and get the same effect, reduce your dose lead to reduced toxicity, which is very important in cancer chemotherapy. Okay, let's go further. It also calculates dose reduction index at your particular data point, actual data point. It also graphic FAC, dose reduction index, DRI plot here. The combination, this is for drug 1 in the combination, drug 2 in the combination. This 1 means no drug reduction. Anything above 1 is dose reduction. It's favorable. If below 1, it's not favorable. And also they plot in logarithmic form. And this is isobologram. Isobologram, the idea empirically obtained over almost a century ago, but there were no theoretical basis. Chou and Tale was the first one to derive the equation, general equation for the isobologram. At all time, you need to spend 2-3 hours using graph paper, extrapolation, interpolation, and graph of the isobologram. Now we can do this in a split of 1 second to construct isobologram at any effect level you select. So automatically it come out. At the end, the computer gives you a summary table, tell you abbreviated form, the experiment name, file name, date, description, drug 1, drug 2, what's the basic parameter for potency, the shape, and conformity to mass action law, and also give you a CI value at different effect level at the IC50, IC75, IC90, IC95, even IC97. So this is the computer printout. So this for 2 drug combination. Also, we can do the 3 drug combination if we want. Actually, I have an equation even for n drug combination. All the theoretical aspect published in Pharmacological Review in 2006. This paper published in 1994 in Journal National Cancer Institute. This paper was listed in my earlier slides, and this was highlighted with editorial, and I also use this data as a supplement in appendix in my Pharmacological Review, Appendix 4. So I want to show you here how to do the 3 drug combination. Okay, we try to combine Taxol with cisplatin with topotecan, A, B, C, 3 drug. Drug A, dose effect, drug B, dose effect, drug C, dose effect, and you calculate MDMR parameter. And for combination, this can be for, in other words, this 2 drug and 3 drug combination we did at the same time, so we can share some data point. So this A, B, this A plus B, dose effect combination. It calculate also parameter and calculate CI value, tell you this exact data point, how much synergism. You can see it's very reasonably smaller than 1 synergism. And B plus C, yeah, this is the CI value. And then A plus B plus C. Oh, A plus C, I'm sorry, this is A plus C. And then it's a little bit additive, and A plus B plus C. So this whole thing was published, crude data, and the computer can generate all this in a few seconds. May take a few minutes to print it out, the entire report. At the end, in footnote here, it shows you can do it manually. If you don't have computer software, you can do pocket calculator, even a piece of paper and a pen, but it may take a long time to do it. That's 3 drug combination I just mentioned. Here is the summary table. It says what combination plus Taxol plus cisplatin for topotecan, and 3 drug combination, and your combination ratio. Here you can see the 3 drug combination are 1 to 100 to 10, A, B, C. A and B, B and C, A and C identical to this. So you can share the data and calculate CI value. You can see from 50% to 95% how much synergism. You can see all across is synergistic. The slide here is additive. and also dose reduction index. Is all greater than 1 is indicate is favorable dose reduction. It reduces many-fold and get the same effect. And this we can also get the individual graph for publication. It's almost ready without going through our department and use straight for the. So there are a lot of things, and this contains the report for this 2 and 3 drug combination I just mentioned, and I don't want to spend time. This is a graphic, isobologram, DRI plot, and they have all that dose effect curve, everything. So it's all there. So much about actual use of the software. I'd like to spend a little time to talk about theory. It's quite complicated, and I only give you very brief outline. Okay, the theory, as I indicated, the median effect equation I derived 32 years ago is become the unified theory for mass action law because it can be used to derive major biochemical, biophysical equation from this equation, like Michaelis-Menten equation, Hill equation, Henderson-Hasselbalch for pH ionization, Scatchard equation for receptor binding. So this equation must be correct, otherwise textbook need to be revised or rewritten. This is the citation of the theoretical paper. It's in 170 different papers. Okay, the median effect equation, as I said, it can linearize dose effect curve. Some are very sigmoidal, some are more hyperbolic. All become a straight line with the median effect plot. And this axis intercept is ED50, LD50, and the slope is described, ABC slope describes the shape. This median effect plot introduced by me about at the same time, so it's very useful for any drug regardless of mechanism of action or what the mode of action. This is the algorithm for computer simulation, how all that report generated. The median effect equation rearrange. From dose, you can calculate effect. From effect, you can calculate dose. This combination index equation is derived by Zhou and Talalay, and this dose reduction index. By substitution, and then it comes out combination index or dose reduction index. And this can be not only for 2 drugs, it can be for n drugs. Here, how much is synergism is synergy? Because people say synergy, it can be tiny synergy, it can be very strong synergy. So this is my recommendation. The dose range of combination index from 0.9 to 1.1 is nearly additive. Slight synergism, moderate synergism, strong synergism, very strong synergism, and same thing for antagonism. And this is a color and graphic line for the graphic. So this is a recommendation. So everything is quantitative. Okay, let's go to animal drug combination because it's important, but here I want to give one example which I reported last year, AACR meeting in San Diego, in mouse xenograft in new mice. The most important feature of this method is using small number of animals. Some other method using 500 mice. And I use 65 mice. This tremendous saving in time, effort, resources, and laboratory animal because the power of the median effect plot is not empirical curve fitting. We are fitting dose effect relation to mass action law, not like a statistical method. It's nothing to do with directly related to statistics. And here I give the dose range, of course, near good planning and some homework, route of administration, schedule administration. So this data, actually, just can give you quickly give you example. This is a T compound. There's a treatment tumor size and treatment at different doses, the dose effect curve. Enter this into, and this is the combination. Of course, drug B, we have dose effect curve also. And then the computer generated report. I only just total 8 pages. I only show 3 pages, show you how it looked like. And just a summary in your paper for on different day, your combination, how much synergism, how much antagonism. Not every day the same. And dose reduction, how much dose reduction in animal. So just carry out same principle as in vitro, but it's very time consuming and very expensive. The new mice cost $35 a mouse, and here we need 65 mice. But other people, when they do it, several hundred mice, they did not get quantitative synergy determination. Okay, here's a comparison. Compare in vitro drug combination in animal and in clinic. The time and effort, yes, in vitro take 2 weeks, 2 months, 6 months to a year. And the material cost, tremendous difference. Sample size is millions, there's tens, this is also tens. And I make a very strong point here. In vitro is easy to do and can quantitate synergy. Animal is difficult, expensive, and slow. Clinic is almost impossible due to ethical, scientific, and practical reasons, which was discussed in my Leukemia and Lymphoma Review article. So, I question FDA actually, if they don't have definition or did not do preclinical experiment, how they allow to do that in human? That is very bad practice. That is very strong criticism in my review article. Okay, here, more detailed comparison in vitro, in animal, in patients. Dose density, population size, variability, R value, and the M value parameter, conclusion available, just quantitative, this is not practical, not applicable. Length of time, 2 weeks, months, years. Flexibility, death as an endpoint is always in vitro, frequently in animal, but human you cannot death as animal as an endpoint, of course. And ethical liability is none, is low, is very high liability for human. So this is a comparison. Here I have a very strong statement here. An open issue, is it ethically acceptable or scientifically correct to conduct drug combination trial in human without first doing drug combination in vitro or in animal? So this is my open question. So this method has a variety of good features. The best feature I did not mention here is allow small size experiment which save a lot of time, effort, resources, and laboratory animals. This computerized simulation of synergy is quantitative. It answers the following primary question. Are there any synergism? How much synergism? Synergism at what dose level? Synergism at what effect level? How the isomogram look like? How much dose reduction allow for each drug for the synergism? other questions depend on your experimental design. You can answer the optimal combination ratio. Is 1:1 or 3:1, 1:3 is the best synergy. Schedule dependency. Is every drug given simultaneously or one after another? Selectivity or synergism. When you got synergy against the tumor, for example, are you synergism against the host? Since the toxicity synergism will be in big trouble. And condition-directed synergism. At a different temperature, different pH, different environment, how that influence the synergism or antagonism. So, this is the conclusion. The Chou and Tare drug combination index is regularly derived and widely used, which is based on mass action law. We have quantitative definition for synergy. Synergy is smaller than 1. Ci is smaller than 1. Equal 1 is additive. Greater than 1 is antagonistic. And the Ci plot and the isobrogram are the only valid graphic for its determination. Drug combination study in vitro is fast and efficient. In animal, is slow and expensive. Based on scientific, practical, and ethical reason, it is not possible to determine synergy in human. And thus, prior to drug combination in clinical trial, preclinical drug combination study in vitro or in animal should be carried out to obtain the basis and rationale for drug combination study in humans. And this is stated in my review article. And this is just a graphic in my review article, the computer generated. This is for simpler illustration. This is a pharmacology review article, which is 61 pages. The top journal, number 7 of 3,000 journals. This give me 61 page length to publish this review article. And this is the general equation for 5 drug combination. It looks complicated. Computer can take that in less than a second, do the simulation. This N drug combination equation. All these equations are in my pharmacological review article. Okay, and this is the contact information. Thank you for your attention.